All right, so now we're going to start talking about chemical reactions. And so naturally, the first question you might ask is, why does a chemical reaction occur? And the answer to this question is the same as the answer to why does a ball roll down a hill? All right, so if we think about a ball rolling down a hill, all right, I've got my hill right here. If I place a ball right here, it's going to roll down and it's going to go down into this bottom of the hill and it's going to end up there. And so if we think about it, this is a minima, right? It's the smallest point here. And so if we think about this as potential energy, the ball will end up in this minima. And so that's the same thing with chemical reactions. They occur to get to a lower potential energy. And so it's pretty obvious to tell with a ball kind of what the potential energy is, but what's the potential energy in chemistry? And so to visit that, we go to the second law of thermodynamics. Which states, or approximately states, that the entropy of the universe or any closed system is always increasing. And so anything that happens because it increases the entropy of the universe. And so if you think back to Gen Chem, what is entropy? Essentially, we call it randomness or disorder. We'll get into more of that in a little bit. But basically, for any spontaneous reaction to occur, and a spontaneous reaction is something that occurs under the conditions of interest or without outside interventions, right? So under these conditions, it's just going to happen by itself. You don't have to do any extra stuff, right? So for any spontaneous reaction, the entropy of the universe is increasing. However, it's hard to talk about the universe, right? The universe is a lot of stuff. And so we only talk about the system, right? So universe, hard to talk about. And so we're just going to talk about our system. And so there's an equation here that says the negative T delta S, the negative of the temperature times the entropy of the universe, is going to be equal to delta G, right? And this is true under constant pressure and temperature. And so this delta G is Gibbs energy, or Gibbs free energy, if you want to call it that. And that's what we're going to use to determine whether something's spontaneous or not. So if something has a delta G that's negative, then it's spontaneous, right? If this part right here is positive, there's this negative number here. So in order for the entropy of the universe to increase, delta G must be negative. And then vice versa, if delta G is positive, we say that that's a non-spontaneous process. And then there's some extra verbiage. A spontaneous process or negative delta G is called exergonic, while the reverse is called endergonic, similar to exo and endothermic, right? So when we're thinking about our ball rolling down a hill, but instead of a ball this time, we're thinking about some kind of reaction, right? There's going to be a spontaneous direction. It's going to go towards lower delta G, and a non-spontaneous reaction, right? The ball is not going to roll up the hill. The reaction is not going to go up the hill by itself. And another equation for delta G, right, where we're just relating it to the system, the delta G is equal to the enthalpy of the system. So the delta H minus the temperature times the delta S of the system, right? So the Gibbs free energy is equal to the enthalpy time minus the temperature times the entropy change in the system. And we'll explore both of these in a little bit.